All right, ladies and gentlemen, this is Chapter 9, Section 9-1, and this is recording number 1. Okay, I thought what I would do is try to make a comparison to current events, or take an example from current events. I thought that might make things a little more interesting, so let's see how this works. It is absolutely impossible for you to not be aware of the pandemic that we're going through. And perhaps if you follow the news, you saw something the other day about a uh, a certain medication that has been granted what is referred to as emergency use authorization. It's not a FDA approval, it's just authorizing the use. And this is this drug remdesivir. So here's an article that I picked up on the internet talking about this. And so let's see if we can find some relevance to our class in this event. So let me remind you that Chapter 9 is hypothesis testing, but now we're going to do hypothesis testing where we are going to test the difference between two means, or perhaps we're going to test the difference between two different proportions or two variances. But the key distinction between the Chapter 9 techniques and the Chapter 9 scenarios is that we're comparing two samples, whereas in Chapter 8 we were taking a sample from the population and we were asking the question, does this sample differ significantly from the population? So if the sample does not differ significantly from the population, we say that the sample belongs to that population. On the other hand, if the sample does differ from the original population, we say that the sample does not belong to that population. Another way of saying the same thing is we say that this sample that I picked from the original population truly belongs to a different population. So that's where you'll see those curves where you have two different curves or two different distributions side by side, one of them differing from the other in a significant way. Okay, so let me pause this. Okay, so here's a web post from the Washington Post. Let's see, it's very recent, 21 hours ago. Today's date is May 2. So roughly speaking, May 1, May 2, this was posted. And I think this is worth spending a little bit of time on. It kind of illustrates what we've been talking about in a couple of different things. The headline here is that the government researchers changed the metric to measure coronavirus drug remdesivir, I'm not sure how to pronounce that, remdesivir, during a clinical trial. So a metric is, in math, it just means some way that you are measuring something. So what they're saying is that the thing that we were measuring changed during the clinical trial. In a statistics class, I think what we would say is the random variable. So we changed the random variable that we were going to be measuring. And here's where they talk about that. They talk about how the investigators changed the primary metric. In other words, they changed the random variable that they were concerned about. Okay? All right, so we'll let you read that. Okay, so now here's the distinction. So this illustrates how important it is to be able to clearly articulate what is the random variable that you're dealing with. So it says, instead of counting how many people taking the drug were kept alive on ventilators or died, among other measures, the National Institute blah 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 said it would judge the drug primarily on a different outcome, how long it took surviving patients to recover. So let's take apart that sentence here a little bit. So if these guys were taking Mr. Cantrell's statistics class, I would say they didn't do a very good job of articulating what is the original random variable and what is the new random variable. So the sentence is a little bit convoluted, a little bit hard to read, but what it's basically saying here is that originally the random variable is survival, or counting the number of survivals. So it's kind of like flipping a coin. You know, is the random variable getting ahead, or is the random variable the number of heads? In this situation here, it's the random variable is counting. You are counting the number of people that were kept alive. Okay, so random variable, number of people that kept alive. And what they're saying is that was the original random variable. And then they say here, instead of using that as a random variable, it's going to be how many days did it take for surviving patients to recover. Okay, so you see the distinction there. The first variable is how many people survive, what number, and then the next random variable is how long did it take to recover. Okay, so the first random variable that has been used, in the past is talking about how many people live, how many people die, whereas this one only looks at the people that did survive, and it's asking the question, did people survive, or I'm sorry, the people that did survive, did it take them a shorter amount of time or a longer amount of time? Okay, so that's the distinction. And here they talk about how, the people dying was kind of moved to a secondary measure. We're going to only look at the people that did survive. So that's what the change was. Okay. Now here's a justification for it, which, I'll leave you to decide whether you think that's a legitimate justification or not. But here's the outcome. Remdesivir reduced the time to recovery for surviving patients from 15 days to 11 days. Okay, now what you're going to learn in chapter 9 is, okay, this is a comparison of means. Okay, the time of recovery, the average time for recovery for the placebo group, for the group that did not get the medication, was 15 days. If you were in the group that did get the medication, it was an average recovery of 11 days. So you went from 15 days to 11 days. So that's an improvement, obviously. Okay, it's 1/3 better, roughly speaking. Okay. Okay, but now here's what you need to understand, and we'll see this as we go along. I'm just trying to give you a little bit of a preview here. In order to really analyze this, in order to decide, well, is this a statistically significant difference or not, you need additional information, which according to this article has not yet been provided. Okay, it says down here that the timetable for publication of the results has not been disclosed. Okay, so we really can't analyze this. I was really surprised that they did not disclose this yet, but that's just the way it is. So what is it that you would need in order to really analyze it? To analyze comparing these means, let me pause this, in order to compare a 15 days on average, so a mean of 15 days compared to a mean of 11 days, maybe that's just due to chance, right? I mean, how do you know? How do you know whether that just happened by random chance? In order to evaluate this, you need to know the variances of either the two populations or the variances of the two samples at least. And we'll see that here in just a little bit. Now, realistically, you're not going to know the variances of the population because this is a brand new virus, and so nobody has any of that information. But you should at least have, you must have the variance or the standard deviation of your sample groups, right? So however many people, I think there's 1,000 people in the study. So the 500 people that were in this first group and the 500 people that were in this second group, you must know the variance or standard deviation of those two groups. If they had published that, every student in this class would have been able to do the the statistical hypothesis testing that you would need to do in order to decide, is this a significant difference, 15 days compared to 11 days. Just based on this information, merely saying, well, that's a 31% improvement, that's not a scientifically valid statement, because you have not told me what the variance is, okay? Now, Dr. Fauci does say here, he makes the very conclusionary statement. A conclusionary statement is where you just draw a conclusion. You don't justify or give the rationale or give the evidence. You just draw the conclusion or state the conclusion. And he says the data shows that remdesivir has a clear-cut, significant positive effect. Now, the word significant here is a word of art in mathematics and in statistics. When you say there is a significant difference, you mean, statistically speaking, it would only happen by chance a certain percentage of the time. That's this error budget that we've been talking about all along, where you have a certain error budget. You say, well, it would only happen by chance 5% of the time. It would only happen by chance 2.5% of the time. That's what you mean by significant. I don't know if that's what Dr. Fauci meant when he said that. I hope so. I mean, he's a professional. He should know what the words mean. But we don't know based on this data, okay? Now, down here, they do talk about significance. So now they're talking like, you know, like responsible adults here. They know what they're talking about. And they say, okay, listen, the difference in death rate, so the average death rate, which is one of the original primary measures. So that, using that random variable, if the random variable is death rate, it says here the difference was not statistically significant. So he knows what statistically significant means, okay? But he just didn't choose to say that up above in the when we're talking about the mean number of days to recover for the people that did survive. And it showed a marginal reduction from 11% if they got a placebo to 8% if they're given the drug. So there is an improvement, but it could be just due to random chance, as we've discussed so many times. Okay, so I wanted to spend just at least one recording on this issue, because I think it's one of the complaints that people always have about mathematics and statistics is it's hard to see how it relates to our day-to-day lives. So here's an example of how it does relate to our day-to-day lives, and I hope that this was of some use to you.